Usually channels are never enough. And everybody thinks about the application of motors because of course normally you want to see the three phases, voltages and currents. But in reality, engineers want to see on mixed domain scopes as much as they can. That means that they want to see analog signals, digital signals, as many as possible.
I think it's more the need that I've seen from engineers who want to see a more system view of their board. So in the past, I think we used to have different domains and each person was characterizing that one domain. But rather today we see more an end-to-end analysis.
So that's why, for instance, our oscilloscope have inputs that you can adjust and set depending on what you need to do, depending on the probe that you plug in, either to be analog or 8 digital channels. So, for example, if you have an 8 channels oscilloscope, this can become a 64 digital channels oscilloscope.
So yes, there are still domains in different engineering cycles and so on, but people also want to see the whole end product and see how it performs. And validating that, you need to see a lot of different domains.
The main address for the 8 channels, that's because the multi-channels need to be due some tiny signals. We need to use a synchronization mechanism when the engineers implement the circuit debugging and retrieving the signals.
The time base is the same for everything. It's very precise. There's no jitter, right? So you can be sure that you can really relate events that happens in time one to the other.
And the most important one is all the 8 channels can be synchronized simultaneously. That means we can use a specific trigger point to see each channel's phase difference and the time difference simultaneously.
And navigate in the history of the acquisition as well, so that you can go backwards and see what happens when some specific data was sent on a digital bus, for instance.
Like the biomedical system, the signals when we use the electrocardiogram, like the doctor to inspect the patient's biomedical signals at their body. For example, just you like to test the electrocardiogram, you have many test points over 8 channels, right?
Motors, as I said, is one of the key applications for multi-channels. You know, when you test motors, you just don't want to measure the voltages and current. You want to know, for instance, what the speed of the motor is. You want to measure the torque, right? All this data from sensors needs to be acquired and to be related in time with what happens with the voltages and currents. You can really connect your sensors output to the scope. Well, actually, we have multiple solutions for that. We have data acquisition systems with multiple channels. You can plug in a card. You can have hundreds of channels. And these cards can really detect signals from any type of sensor. It could be temperature, it could be velocity, right? It could be whatever you need. And all this data, can be correlated with the acquisition of the oscilloscope. So think about FPGA engineers, designers that wants to see how a digital bus correlates with something happens in the analog world, but at the same time they might want if like a RF carrier signal goes up in the air, right? And they want to see this correlated in time. So they want to connect all of this equipment to just one measurement unit, and they can do it with multi-channel scopes.
So you can actually see the frequency domain. So you see your frequency response of whatever you're trying to measure. You see the time domain view. You see the logical messages that go through. So you can use logic probes to actually probe onto an I2C line, an SPI line. So just control signals or so on. Maybe it's a particular message that's being sent. You can find where exactly your problems are in your system by actually setting the scope to actually find this particular message. Okay, what does the frequency look like? What does the time look like? And so on.
For example, just like the Regos MHO DHO 5000 series, we have 4 ADC by 2 channels using the together by 1 and 2, 3 and 4, 5 and 6, 7 and 8. So if we open half channels, that means the sample rate will be divided by one's time. Yeah. But if you open for the full channels, that means the sample rate will be quarterly divided. Yeah. Just like if we use the 4 gigasample per second, if 4 channels, that means we just have the 1 gigasample per second.
Today, the limitations are very minimal, and there is basically no compromise on the bandwidth aspect, for instance, right? So what you just regulate yourself is the sample rate, because maybe you want to have you need for a specific standard to sample, very fast, like 50 gigasample per second. And you can have it, for instance, only on 2 channels, the sample rate.
This high performance of the new oscilloscopes are only possible when all these features are built into the FPGA and the programmable hardware. The processor can't analyze so many data in a short time. The FPGA can parallelize it and analyze a lot of data parallelized, and brings up the performance a lot.
Otherwise, if you want to use all channels at the same time, then you go to 25 gigasample per channel, for instance. So that's the compromise. Of course, that depends on the model that you choose. You want really to make sure that you detect a bursty signal only when the signal is there, and not during the intervals where the signal is not there. You don't want to use the memory. That's why you segment the memory, right? It's called segmented memory, right? So you can basically select the frames that you want to capture the shot on, and just save them, and avoid storing data when the signal is not there, right? And then you can do whatever you want. You can overlap them, and you can have a search algorithm to search for something that has a special shape on these frames that you want to capture.
One really nice tool that we have on our oscilloscopes is a zone trigger. So this allows you, from a traditional trigger point, it's like a level that you have, and the signal should cross that level. But when you don't know where it could be, or what that level is, or so on, or what that shape looks like, you can create zones or shapes, if you may, on the trace itself. And then whenever the signal hits that trace, that acts like a trigger condition. And this zone is actually done in hardware, so it's done in our ASIC. So you still get the really fast performance of the oscilloscope as well. So for example, if we have a EMI issue or so on, we can actually look and monitor the FFT, so the frequency domain, and we can actually set a zone area that we expect, okay, that this signal should never cross this area or so on. We can leave that running over a period of time, and as soon as the signal crosses or we see an interference, we can actually capture that interference and actually see, okay, and if we had everything connected, so logic probes, maybe current probes or so on to monitor the power line, and also our data signals itself, and we're actually seeing everything that's going through, and we can actually quickly identify, oh, this message was sent, that's the wrong message, if you like. Very infrequent message that comes through, it shouldn't have come through, but it's there, it's been caught, and it's exactly at this point when we see an interference happen. So we can identify just by having this whole system view of this multi-domain capability.